we realized that an extended body undergoing an inelastic collision is just too complex a thing to model as a simple point mass. The real problem is that even if the wall here were able to move, like if the block were hitting another block that was also moving, the real problem is that if this block deforms at all, if it changes shape at all in a non-spring-like way, then some parts inside the block will be pushing on other parts inside the block, and there will be this internal dissipation of energy. And that internal energy dissipation requires more sophisticated physics to model properly. We just can't do it with our simple work energy theorem. So this does not hold for our extended body. And if our work energy theorem doesn't hold, then our version of conservation of mechanical energy doesn't hold either, since this was derived directly from that. So we have to throw this out as well. So we seem to have reached a cliff, a metaphorical cliff, in our ability to analyze the physics of this scenario. But there is a way to save ourselves. And we already had a hint of it right here when we thought about the impulse imparted to the block by the wall. The wall does no work on the block, but it does impart an impulse. So when energy exchanges get too complex due to a deformable body and internal work that's dissipating energy as heat inside the object itself, when those energy exchanges get too complex, we can just stick with momentum instead. So here's our collision. Once more time. Block hits the wall. There's the center of mass of the block. There's the velocity of the center of mass, the velocity of that one point. Here in yellow is the little dm that's actually in contact with the wall, and there's our red contact force from the wall. If we write down Newton's second law for a system, N2L for a system, you know it in this form as it relates to acceleration of the center of mass to net external force. If we write it in terms of the momentum of the system, we have the rate of change of the momentum of the system is equal to the instantaneous net external force. So I'm going to take this equation and rearrange it a bit. This is all about momentum conservation here. I'm going to flip the sides and then take the net external force and dot it with the instantaneous velocity of the center of mass. I'm dotting these two vectors together and then dotting both sides of that equation by the velocity of the center of mass. Then I'll multiply both sides of that equation by dt, move the dt up here, get rid of that dt on this side, and note that our VCM times dt, VDT is just dr, so the VCM times dt can be replaced with dr cm, that is the instantaneous infinitesimal displacement of the center of mass, little displacement of that center of mass as the block moves. On the left-hand side, the momentum of our system here is defined as the total mass of the system times the velocity of the center of mass. So dp system here can be replaced with m system times d VCM, a small change in the velocity of the center of mass. So on the right, I've got the VCM dotted with a small change in the VCM. Okay. Now I'm going to integrate both sides. Each side represents some small change. I'm going to add up all those small changes as we move along the path taken by the center of mass. As the center of mass moves towards the wall, as the block crumples in its collision, that's the path the center of mass is taking. Look at this dot product here. This looks like a force. It is a force dotted with a displacement, which we think of as work. But this is most definitely not work right here. Let's be very clear on why. The force is acting on this yellow dm that is actually touching the wall. The contact force can only push on something it is contacting. It's contacting this little dm. So the force is acting on this dm. But what we're doing is dotting that force not with the displacement of that yellow piece, which is 0 anyway. We're dotting that force with the displacement of the center of mass. The force is not acting at this point, but we're computing this integral as if it's a work being done, as if that external force were acting not here, but here. So it's a bit of an imagination game here. We're imagining that this force, instead of acting at this point and pushing on this, is acting here. And this point, the center of mass, it actually moves. So if we dot this force with this moving mass, we can actually get a non-zero result. Something that looks like work, although it's not work. Because work has to be done by a force pushing on the thing it is actually pushing on. It's acting on this point here, not on this point here. And so we have a thing that looks like work, but is not actually work, because the force is not acting at this point. Nevertheless, we can keep doing the math. On the right-hand side, we have the integral of the VCM dotted with the VCM as we go from some initial value of the VCM to some final value of the VCM as the center of mass moves along its path. The right-hand side here, we've done an integral like this before with this dot product back when we derived the work energy theorem. We can show that this is equal to, our antiderivative here would be 1/2 times the speed of the center of mass. So, squared. And we'll evaluate that at the initial and final values of the speed of the center of mass. So we get 1/2 times the mass of the system times the final value of the VCM squared minus 1/2 the mass of the system times the initial value of the VCM squared. Terms that look like kinetic energy. Our system here, by the way, in case it wasn't clear, is the block itself. The extended body is the system. So I'm going to rewrite our left-hand side and our right-hand side now. I've gone through this derivation, setting up something that looks like work, even though it isn't work. What we've done is rearranged Newton's second law for a system into what we might call the pseudo-work energy theorem, where we have this thing on the left-hand side, which looks like a work but isn't a work. We'll call it the pseudo-work instead. The pseudo-work done by the net external force on the center of mass of the system. It's not real work because this net external force doesn't actually act at this point. These external forces act in general on other points. But we're setting this thing up pretending as if the external forces were actually acting right at the center of mass. And it's perfectly okay to compute that this value here. It's just that it's not real work. We'll call it pseudo work. And then here on the right, we've got the change in what we'll call the KCM. 1/2 the mass of the whole system, which would be the mass of the whole block, times the velocity of the center of mass squared, the speed of the center of mass squared. This is a momentum principle. Since it came from Newton's second law, this is a momentum principle disguised as an energy principle. And since it's actually all about momentum, that's why it involves external versus internal forces, as opposed to conservative versus non-conservative forces. If we were really talking energy here, we'd be talking non-conservative versus conservative. But this is secretly all about momentum, so that's why external forces versus internal forces is the important distinction. Note about the KCM. This is not the total kinetic energy of the system. It might look like it, but it's not. After all, the parts of the system, all these little slices of mass, are all moving at different velocities. So the total mass of the system is definitely not moving at this speed. This is just the speed of the little bit of mass at the center of mass. So this is not the total kinetic energy of the system, although it looks like it. It's actually more like this example. I think this example illustrates it. You may recall, if we have a rolling wheel that's moving along, the kinetic energy of our rolling wheel has two terms, what we call the translational kinetic energy and the rotational kinetic energy. The translational kinetic energy, 1/2 the mass of the wheel times the VCM squared, that is exactly identical to what I'm calling here the KCM. KCM and K-trans, those are the same thing. And note they're not the total kinetic energy, or at least not necessarily. Because if the wheel is spinning, if it's rotating, it also has this rotational kinetic energy given by 1/2 times the moment of inertia times the angular speed squared. So this would need to be added to what we're now calling the KCM or the K-trans to get the total kinetic energy. All right. That's part of what I mean when I say this is not actually an energy principle here. It's not about relating all the energies. It's really just about relating momenta and a specific part of the energy of the system. Okay. So a lot of introduction there about a strange idea called pseudo-work. Let's now apply the pseudo-work energy theorem to our inelastic collision between that extended body and the rigid, immovable wall. Let's see if we can use this idea in place of our standard work energy theorem, which applies to point masses only. This pseudo-work energy theorem can apply to our whole extended body. So here's our block approaching the wall. There's the center of mass, VCM, initial VCM to the right. Then let's say sometime later, the block has fully crumpled, crashed, and come to rest. And the center of mass has moved this distance forward. Now each little bit of the block moved a different distance, but the center of mass specifically moved this distance. That was its displacement. So here's our pseudo-work energy theorem. Here's the pseudo-work, the net external force dotted with the displacement of the center of mass equals the change in this KCM. Okay, final KCM is 0 if it comes to rest. Initial KCM was the 1/2 times the mass, total mass, capital M there, times our initial speed squared. So that's the right-hand side. And then here's our left-hand side. This equation correctly describes the collision. This is what we've been looking for. This is our answer to the problem of an extended body in an inelastic collision. What you could do to analyze this integral here is, say, replace it with the average value. Since an average value is always defined in this way, we can replace this integral with respect to position with the average value of that force exerted by the wall, that external force that was from the wall there, the external force from the wall, dotted times this delta x. So replace this integral with the average value of the integrand times the delta x. And this typically would be the equation you actually solve. You would either be given the average value of that force, or often you'd just be assuming that it was some constant value times that displacement. That is a way to calculate the conversion of all this kinetic energy. Just the KCM kinetic energy, not any other kinetic energies that might be there due to rotation or temperature. The conversion of that KCM into heat in the collision. To look at the full energy transfers involved with, say, rotation and whatnot, you might need some thermodynamics. This result, I'll note to conclude, is equivalent to using the impulse momentum theorem for a system, because this is actually all about momentum here, even though it looks like energy. Our impulse momentum theorem, that's this here, we could apply that to our collision. We had started to do this earlier. That external force, the contact force from the wall acting over time, is non-zero. And our change in momentum of the system is just the final momentum 0 minus the initial momentum of the system. And so you might replace this integral with the average value of the contact force times the change in time. Although that would give you this result to work with. But I would note that this average value would be the time averaged value of the force, as opposed to this, which would be the position averaged value of the force. Since, after all, the average of the force with respect to position, this integral, is not necessarily the same thing as the force average with respect to time, this integral. So these could, in principle, be two different values here. Although if the force was, say, constant in a really oversimplified result, these would be the same constant force if that force was indeed constant. Okay, I think that wraps it up. We'll be seeing in the future additional opportunities to utilize this pseudo-work energy theorem when we have an extended body with complex internal energy exchanges that are just too tricky to handle with energy. So if we've got some external body, if we just want to deal with a momentum-based principle for it instead, we'll be utilizing this pseudo-work energy theorem.